Hello. So, as he said, my name is Andrew Gray. I'm one of the lead engineers for Charter Communications. And I wanted to talk to you about yet another traffic engineering presentation. But this one is different. This one is not going to talk about the technical minutia of RSVP or segment routing or anything like that. This one is focused more on how you decide which way to go. These are different technologies. They have different use cases, what have you. This talk is talking about our journey through a recent reevaluation of where we're at. And I encourage everybody to go through and do either an initial evaluation or rethink what you're doing every 12 to 18 months. Technologies always change. But this deck is going to be talking about one of our recent forays into going through that process. Like I said, please don't take this deck as this is the way Charter's doing it, so this is the way everyone should be doing it. That's not the intention. The intention is to walk you through how we got to where we are. But first off, the question is, what did we actually need from traffic engineering? And that almost immediately devolved into the question of what is traffic engineering? Because you ask 10 people, you'll get 14 different answers. So for the purposes of this conversation, we're calling traffic engineering any mechanism that manipulates a traffic flow other than what basic IGP and BGP says to do. Anything above that, we're chucking into the bucket of traffic engineering. And most of you will realize that's fairly broad, and you'll see why here in a little bit. But as we started going through this, we actually realized we need to nail down what these problems are that we're actually trying to solve. So I want to go through a couple of these example problems that we had. The first one is we need a solution to suboptimal traffic routing. So what do we mean by this? All cities and fiber paths and everything else are completely fictional. I literally made these up by throwing a dart at the wall, but we'll start with that. So we're picking on two cities, Indianapolis and Chattanooga. Okay, that's great. We pull these back to pops. Indianapolis goes to DC and Chicago, and Chattanooga goes to DC and Atlanta. Now, if we have a customer who's in Indianapolis and has another site in Chattanooga, and they want to talk to each other, a normal customer will go, hey, that's 520 some odd kilometers as the crow flies. My time should be very quick between these two sites. But as we all know, network-wise, that's never the case. And in fact, the direct path, if you go through DC, is about 1,800 kilometers. So already we're 3.5 times longer than what the customer is expecting. But that's if we get the best case. That's what happens if Indianapolis and Chattanooga both pick DC. What happens if we go the other way? What happens if we do the worst case, where all the traffic into Indianapolis goes through Chicago, and all the traffic coming into Chattanooga goes through Atlanta? Okay, that's fair enough. Of course, we've got a path there. But we go from Indianapolis to Chicago, we go through Cleveland, Philadelphia, DC, Durham, and then back around to Atlanta. A very suboptimal path if you're worried about delay. In fact, you add on about another 11 milliseconds over what you would just see from the straight path. Oh, but wait. It gets worse. So let's say Chicago to Cleveland takes a hit. Our customer, remember, is still expecting this 520 kilometer path. But if we take a hit Chicago to Cleveland, Indianapolis may not necessarily reroute. Instead, it depends on Chicago to reroute. And that's fine. We're an ISP. We've got a backup path. So we're going to reroute them through St. Louis, Kansas City, Oklahoma City, Dallas, New Orleans, Birmingham, and around to Atlanta. This is obviously much longer than what they would expect from their direct path. And we can solve a lot of those problems if we can just assure that DC will be the first choice of output. Let's talk about another problem. So again, I'm picking on Indianapolis here. And in this case, Indianapolis has 330 gigs of traffic coming out of it. Okay, we've got 3 paths. We're doing ECMP. We've got 110 gigs down each path. Everything looks fine until we take a hit between Indianapolis and Fort Wayne. Okay, again, we have ECMP. That's what this network is designed to do. So we fail over, we take the 110, we split it up 55-55, we toss it over towards our links towards Nashville and Cleveland, and it all seems okay. However, if we go down one more notch and start sending that 55 gig southbound, oops, now we've got a problem at Nashville. We've overloaded that link. We got plenty of capacity over at Cleveland, but how do we manage to manipulate the traffic in that fashion in order to relieve that? Another issue that we have is we need to handle exceptional traffic differently than what routing says. Again, we're an ISP. The large majority of our traffic is simply trying to get on or off our network as quickly and cleanly as possible. However, there's always that certain traffic. Those customers are paying for business grade circuits that want very low latency or have very high requirements, and we're charging them for it. So we should be able to deliver to it. So in this example, I have customer A and customer B, and let's say they want to talk to each other. If we put some delay times on here, you see that their delay, if they have to go all the way up to our regional, is 34 milliseconds. If you're talking about some of these technologies are expecting 10 or 15 point-to-point, that doesn't really work. And again, if you look at it on a map, why is it taking so long? So of course, we can always add in a bypass path. Maybe it's a lease circuit, maybe it's something else, maybe we have to go trench fiber, who knows? But let's assume that it's expensive and low capacity, and most importantly, we don't want our commodity traffic to take it. We need some way to differentiate that special traffic to take the special links. Fair enough. Of course, everyone wants fast reroute. Current goal is always 50 milliseconds. You've heard that for probably a decade or more. And it is a good goal, and it's based on reality, because after that, you start suffering in things like your voice traffic, your video traffic. You start seeing a lot of issues if you take longer than that to reroute. However, 50 milliseconds is for today. In the future, we're seeing technologies like 5G and some other things that will require much faster failover times and restoration times on the order of 10 milliseconds, which at a certain point, physics says you can't do. But we need to be able to engineer a network to be able to do that as often as we can. So those were some of our main cases. There's probably more, but there's always wrinkles. There's always complications to how you're doing that or things that you need to worry about. And in our particular case, we've got a couple of these that are worth mentioning. The first one is Charter is the product of some acquisitions. So we still have a lot of different BGP ASs running around on our backbone. More problematically, we have a lot of different separate IGP instances running around. How do you get traffic engineering data through? You can use BGP-LS, of course, a lot of people do that. Or do we bother spending the time to combine all those BGPs down to one and combine all of our IGPs? But then you start talking, well, okay, now I have an ISIS domain that crosses the entire network. What's my route scale? What's my loading? What's my failover time? This is not a trivial choice to make. Multicast. We're a cable operator. We deliver linear video through multicast. And most problematically, we deliver this via one source to hundreds or potentially thousands of receivers. It'd be really nice if whatever traffic engineering solution we come up with can also protect our video traffic. If we're going through all this engineering work, let's try and cover as much of it as we possibly can. This one kind of crept up on us a little bit, and this was hardware MTU. I'm picking 9192 here because it was fairly common, but we've all seen kind of the 9216s or what have you that you may see in your particular networks. However, we had some very, very old circuits that if you went back and looked through at the way the contracts were written, we potentially allow a customer IP MTU of 9100. We start running out of frame size very, very quickly at this point because you start adding on customer framing, you add on network framing, that leaves us only 56 bytes at the end. We've got potentially 56 bytes in our packet to play with. That's enough for about 14 MPLS labels. SRv6 starts getting a little cramped, though, at that point. Now, mind you, we don't usually sell circuits like this. We normally follow this industry standard of 9,000 byte circuits. And there's a question, are the customers actually using this? Is this something we can go back and renegotiate if we need the space? Probably, but that's a lot of extra work. Can we avoid it? What do we not need? And this also tends to be somewhat important. What we don't need right away is inline network programmability. And by this, I mean some of the very interesting work with SRv6 and the SIDs and being able to do some of the network manipulation in line. In the end, we're a backbone. The use cases for that get a little obscure. Now, in a draft of this, when I was going through this, someone mentioned, oh, are you talking about netconf and openconfig? Absolutely not. We desperately need those, and if only openconfig were actually in a usable state today. However, as we sat around and did a lot of brainstorming about this, we can see on the distant future if we start going to some esoteric arrangements where some of this functionality may be useful. But one thing we notice, especially in talking to some of our peers, is generally we're a bunch of network engineers who started off in the network engineering field and we've picked up programming along the line. You talk to people who've come up the other direction. They started as programmers and pick up network engineering. And you get a difference of not so much opinion, but just a difference of perspective and what's important and what's not. So if you can, get a good mix of people in there. Get your engineers, operators, get everybody kind of taking a look at this. Another thing that we decided we don't really need right away are very fancy controller capabilities. And what I mean by very fancy is things like really esoteric scheduling or what have you. Yes, we potentially need some basic controller capabilities, but our needs are fairly mundane. However, the big problem that we need is we need multi-vendor support. And this gets very iffy. Generally, if you're dealing with vendor A, they want you to use vendor A's controller. And maybe they work okay-ish with vendor B, but what about vendor C? What about white boxes? You start asking these questions, and the answers come back very mumbled indeed. And there's always this whole controller part. Been in networking for 20 years now, and you get to this point where you have what seems like this magical black box that wants to drive your network. We've all been around long enough where we've seen incredibly esoteric bugs or strange bugs show up in just normal routing systems that have been around for 20 years, have had some of our best and brightest working on this the entire time and troubleshooting that. And you want me to hand off control to this thing? Maybe. I kind of like the idea, but So now that we've kind of outlined what our problems and what some of our restrictions are, let's go through what some of the possible solutions are. This next slide always makes everybody groan, but it is worth putting on there, so we could do static routes for most of this stuff. I'd rather personally not, mostly because you run into the same problems you always do, documentation. Yes, vendors have various comment or annotate or what have you that help with that. But again, you come back to something 12 months later, you're redesigning that part of the network. What is this static route for? What is it doing? Is it even still needed? Who knows? It is a very coarse mechanism. And yeah, we can solve a couple of our use cases like this, and probably do, but that's not a good way forward. Next one up is IGPS MED. Now, I recognize this is not a normal traffic engineering protocol, but remember how I defined traffic engineering at the start. And yeah, IGPS MED technically plays with your IGP weights, but it's not your normal default routing type situation. And if you remember my problem at the start with talking about traffic exits, IGPS MED does a very good job of this. If we just re-advertise the backbones metrics into the markets, you can see we'll advertise in from DC, hey, I'm directly connected, my MED's 10, so please use me. Chicago and Atlanta advertise in much higher metrics because in this particular diagram I'm figuring so many per hop. And so now Indianapolis and Chattanooga now have some guidance as to which way to go. This does solve some of our problems, but it's not a complete solution. Anytime you talk about IGPS MED, you almost have to talk about its other cousin, AIGP, or accumulated IGP. If you look at this, it seems almost tailor-made for our particular problems. We have multiple BGP ASs. This thing will allow us to just build up the metrics all through the path. And again, the same thing happens here. Chattanooga can advertise out, hey, 50 to me, because I don't really care which way you come in. And then the backbone can add on its own metric. DC says, hey, you're directly connected, I'm going to add nothing. Chicago says, hey, I'm going to add on a lot because you're a long way away. And again, Indianapolis, in this particular case, knows how to go. It's somewhat similar to MED, but we had a pretty large concern about it. This is a summary of 3 different vendors' BGP tables, and I'm sure if you look at it, you can figure out who's who, but we're playing nice and we're anonymizing all the vendors. However, the parts here of concern is that AIGP occurs before shortest AS path. We already use AS path prepend to manipulate traffic on our network, so if we go this way, we've got to go through and clean that up as well, or figure out what happens. What happens with our customer circuits when they themselves are advertising in longer AS paths into us? How do we adapt to that? But one of our other bigger concerns with this is the fact that the only other knob we're left with after AIGP is local pref. And that's practically a sledgehammer, and that kind of rubbed a lot of us kind of the wrong way. It's one of these things where like, yeah, it probably should work and we probably will be okay, but if we have IGP as MED and it seems to solve the same problem, maybe we should go with that because that leaves us a few additional knobs to turn. Now going into the actual traffic engineering protocols, or at least the ones that are commonly referred to as that, we start with RSVP. Not going to lecture everybody here about what RSVP is, but it has been around for 20 years. There's been lots of work to standardize and do interop testing on this one. It has point-to-multipoint capability, and it has the ability to do traffic engineering by some extensions. RSVP does require an additional protocol to stand up, but only one in our particular topology, because we already have MPLS and LDP. So we turn on RSVP everywhere, and we would be good to go. Okay. Talk about RSVP, you almost have to talk about segment routing in almost the same breath. And segment routing is a very interesting protocol, but it's still in draft status, which raises a couple eyebrows, especially as you try to sell this upwards. Yes, it doesn't really mean that they're going to be doing a lot of changes, and people will say, hey, we change RFCs as well. And this is true, but normally when changes to RFCs come through, you're more worried about backward compatibility, making sure your existing deployments are good, as opposed to in drafts where theoretically, they could change the entire thing out from under you. With segment routing, admittedly, this is probably not going to happen. They're on draft 15. It's pretty well settled down, but it is a concern. Segment routing, practically for our usage, requires the use of a PCE. And I'll talk about PCEs here in a couple minutes, so I don't want to belabor that right now. In our particular deployment, we would need to stand up two new protocols to support segment routing, BGP-LS, like I mentioned earlier, and PSEP in order to talk to the controllers. There is some interesting work going on with additional BGP families to eliminate the need for PSEP and be able to send that information through BGP, but that's even more in the draft and more in the experimental phase. However, this bottom bullet point was one of our biggest avenues of concern, and the gentleman from Juniper hit about this on Monday a little bit. So we have a customer. Yay, we have customer sends us data, even better. So our segment routing controller says, okay, I want you to stick 4 labels on here and send it onward to router B. Can router A actually do that? Can it actually put 4 labels on that packet? Remember, before segment routing, needing to be able to put 4 labels on an outgoing packet would be a very rare operation. Maybe you need it for some kind of bypasses or entropy label or what have you, but it was not common at all. You would see it a lot of times with legacy hardware limits of 3, for example. We didn't see that in any of our core hardware, but it's something to be concerned of. But keep in mind, it's not just router A you have to be worried about, but it's also router B, because he has the same problem in terms of transit. Let's say router B has 2 hosts, 2 other destinations, C and D, and he's doing ECMP between them, and we're just following IGP to do the routing on our first router or label. Can he actually look deep enough in the packet to get enough entropy to figure out which path to take? He's got to get through 4 labels, get to the IP header, figure out what IP version he is, and then figure out the 5 tuple from there. Again, for hardware that's not designed for this, that is a tough ask. But you say, okay, I can solve that with segment routing, just explicitly set one host or the other. But you still got the same problem with layer 2 and lag hashing, because you've got the exact same computation that needs to occur there. And that's great. So, okay, I'm good for 4 labels. Can you handle 6? Can you handle 8? How many labels do you actually need? And that's a huge question that anybody going through this process needs to answer for themselves. How many labels would you actually need to do all the tricks that you want to do in your network? And can your hardware actually support it? SRv6-TE comes generally in the same breath as segment routing. It's a little more drafty. It has, I'm not going to belabor again, segment routing headers and what have you. You probably noticed on my MTU slide, our main concern is the size of the header, and the fact that we're already running MPLS internally kind of made us toss out SRv6 fairly early on from serious consideration. It is still something we're eagerly keeping an eye on. We're keeping an eye on everything. But for right now, for today, it doesn't seem to be a good fit for our network. Vendor support is very basic at this point. There's very limited hardware acceleration. Only some of the newest chipsets coming out can actually do it, and the older hardware probably never will. PCEs. So PCEs are actually a fairly old technology. They started with RSVP. They've been around for a while. So this isn't in and of itself concerning. However, again, we've got this magical box that's going to be driving our network. How do we deploy this box in a redundant enough configuration where we can trust it to run our backbone? How many sites do we need? 2, 3, 5? What happens if we lose connectivity to all of them? If we lose a metro site and we lose all of our connectivity to our controllers, what happens there? Yes, the specs say one thing. Is that what actually happens? What happens to all the circuits I've set up? From a contract perspective, what happens if I suddenly start violating those SLAs? What's the risk there? Doing that calculation. And we do still have the problem that I mentioned earlier. Generally, vendor A's controller works brilliantly with vendor A, and maybe not so brilliantly with vendors B, C, D, or E. We are keeping an eye on the various open source projects as well, just to be tracking that and potentially being able to deploy those in the future. However, especially for segment routing and even for RSVP, we would view this as almost a requirement before doing large-scale deployments. We can do small-scale deployments solving those individual problems as needed without it, but still, it would be really nice to have. So, conclusions. I would encourage everybody who goes through these same things to end up doing a table like this, and basically you end up with your list of requirements and do my protocol so those requirements. In our particular case, first one was, is it actually available in the code we have deployed? Unfortunately, we do have some older code. We're an ISP, we like nice stable code, so SR wasn't necessarily available. However, we do acknowledge that it is available in currently released non-beta code. So at least we've got an upgrade path, and we can handle a software upgrade, so that wasn't such a huge issue. Does it support traffic engineering for multicast? And this one will raise an eyebrow or two because I haven't X marked an SR because you have beer with SR and a couple of interesting proposals. And yes, but they're not deployed yet, and we can't get that in code. So for the time being, we can't really do it. IGP and MED and AIGP are listed as NA because they're effectively just manipulating the IGP. So multicast will just follow that. So yeah, it's kind of an NA there. Suboptimal traffic routing, as I mentioned, all 5 of these will support it. And especially if that were my only problem I had, I'd seriously look at IGP as MED or AIGP and just avoid RSVP or segment routing altogether. Why add additional complexity to your network if you don't need it to solve the particular problems that you have? Bandwidth management, anything that does traffic engineering will solve this for us. So again, the 3 TE protocols, RSVP, SR, and SRv6 get check marks, and IGP and MED and AIGP, since they just affect overall traffic flow, get access. Ditto fast reroute for basically the same reasons. And exceptional traffic. In order to handle this, we need some way to either do link coloring or preferences or way to specify, okay, traffic from this source goes to this destination. The fact that we need it to be source specific basically eliminates IGP as MED and AIGP. And my requirement that I mentioned earlier that we need to keep the bulk traffic from using those expensive links. Complexity to deploy. This row is very specific to us and has a lot of the dependencies on our current situation. IGP as MED is rated as low because we already have it in some parts of our network, just not all of them, and we need to go through some work and do some consistency and that sort of thing. AIGP would be moderate. We'd have to turn it on everywhere, and we have the concerns about the AS path prepend that I mentioned earlier. RSVP gets moderate as well because, for the same reason, RSVP's been around for 20 years. We've got it in certain parts of our network, so this would be largely a standardization and deployment exercise for us. SR gets marked up as high because not only do we have to go through a firmware code upgrade to do it, but we have to deploy the PCEs as well. And how do we go through and ensure those PCEs are at an acceptable amount of reliability? How do we go through and make sure that we get all the code upgrades done? This is a very long process to do, so that's the reason why it's marked high. And ditto for SRv6. SRv6 would probably be better off at extremely high, but. And last, but certainly not least, is complexity to operate. Yes, we as engineers can sit here and design up an absolutely perfect system, but if the people responsible for actually running our networks can't make it work, it is useless. So taking a look at this, IGP and MED and AIGP are low. It's practically a set it and forget it type technology. Once you get it installed, set up correctly, they do what they're supposed to do. RSVP and SR are moderate, but again, remember my use cases. I'm worried about exceptional traffic. I need to set up occasional tunnels from point A to point B. The huge majority of my traffic doesn't need any kind of traffic engineering support. So if I'm focused on just that, yeah, I can manually set up these tunnels in either protocol reasonably well. SRv6 is listed as unknown, mostly because, like I mentioned, we stopped looking at it fairly early on, so we didn't go this far inside our evaluation of it. Summary. Every network is different. Again, don't take this as gospel. Take this as more of a list of things that we looked at and hopefully add them on to what you guys all go through when you're evaluating these protocols. We are presently planning on doing a couple of different things. There's no need to just say, okay, I'm going to pick this one technology and stick with it, and I'm going to force everything to use this one tool. That's not the best way in the world to do this. We're keeping an eye on SRs and PCEs for future usage because they're obviously where a lot of the work is going on. There are actually some really interesting use cases that will be available in the near future. But again, we're taking a look at what can we do today. We'll go through the same exercise again in 2 years, and a lot of this algebra will probably change. Right now, SRv6 is off our radar, again, because we don't have the MTU to spare, and we've already got MPLS deployed. So with that, that wraps me up. Any questions, comments, feedback?
Steve Ulrich, Juniper Networks.
Hi.
Curious about your evaluation of multicast in an SR environment. In looking at beer or things like TreeSID, did you evaluate the hardware requirements for beer in terms of deployability and kind of what would be associated there?
Yes, specifically with beer in particular, the fact that right now it supports 256 destinations without doing some of the more esoteric things that are currently going through the IETF and draft status. That was one of the main things of concern. The other thing is the different destinations themselves didn't get traffic engineering handling per destination. So those were the two main reasons that we were kind of concerned about it. All right, anyone else? All right, thank you.